And so our first speaker is going to be Owen Duckworth from NC State. He got his PhD from Harvard and did his postdoc at Berkeley, and now he's in soil science at NC State.
Thanks for the introduction, Albert, and thanks to... Wow, that was awesome. I know. Is the piano going to come out soon? And thanks to Ben and others for the invitation and all of their efforts to bring me here today. I'm going to talk to you about something that I've been doing, looking at some interesting environmental processes happening at a local Superfund site, and maybe some ways in which we might be able to use some of these processes in treatment of waste at other locations. So the first thing I like to do when I give a talk is to do, because these are generally the people who actually did the work. I usually just sort of stand around and cheerlead. Mac Jones and Rena Diaz are two talented undergraduates at NC State, and Christian Heath was a visiting RAU student from Bowdoin. Then we have Edwin was a graduate student in chemistry who we worked with, a couple, Megan and Nelson, and then some professors who we collaborate with, Matt Polizato and Leslie Sombers at NC State, and Kara Santelli at the University of Minnesota. With that out of the way, I thought I'd give sort of a 50,000-foot overview of sort of what I do. What I'm really interested in, I'm trained as a geochemist, but I've sort of slowly drifted more towards biology as I've gotten older and more comfortable with uncertainty. And what I'm really interested in is how organisms interact with the world around them, really the inorganic world. So if you think about it, water is sort of at the center of everything because it really mediates a lot of the interaction in biology and a lot of the processes that happen in sort of the near Earth surface. So between plants include the plants releasing chemicals that go into the soil solution. Those chemicals can interact with microbes. The microbes can interact with minerals. Those minerals are the ultimate source for those microbes that isn't carbon and nitrogen, essentially. So any of the micronutrients that need come from those minerals. There's organic matter. That's sort of another there. The plants and microbes and helps hold the minerals together, as well as provide some sources of other nutrients as well. So there's a really complicated web of interactions that goes on between these players, and we're really interested in how this web of interactions happens, what it does to metal ions, and what its consequences for the environment. What we currently are focusing mostly on are biomineralization. That's the process of organisms taking dissolved metals and making them into minerals, and bioweathering. And that's the process by which organisms do the opposite. They take these minerals and they weather them and take what they want out of it to get nutrition. And fundamentally, we approach all these problems in kind of the same way. And what's going on as a process. It's great to have kind of understand the driver of what's going on in the environment, and then understand its output. But that leaves you kind of a black box. We want to get in that black box and sort of at the molecular structure, and dig in, really understand what's causing the happen. So what we'll do, we'll use spectroscopic methods and computational chemistry and microscopy. We look at the way atoms are arranged in space and how they structure to try to understand how that affects reactivity. Same thing with biology. We'll look at how communities are arranged to try to understand how that affects things like chemical reactivity. By chemical reactivity, I mean how components break down, how metals absorb to surfaces, what really affects how things happen in the environment. And then we try to take these things, which are really small scale, really fundamental type process measurements, and we try to relate them to real world problems. So need to be solved, like environmental remediation. Plants grow better with fewer inputs, or right there's a coal fly ash spill that we worked on, trying to understand how to manage the damage caused by releases of waste into the environment. And hopefully that we can get better models to try to understand what happens in the environment and maybe get better management or improve technologies. Sort of today's focus, which is really on and in the U.S., this number is a little old. This number might go down this year, but typically about 18 billion on cleanup of land and water. And there's a lot of technology developed for this, but predominantly across all sites, most strategies used to do environmental remediation to clean up land and water are in ex situ means, meaning they disturb what's going on. Meaning you pump the water, treat it, or you take the soil and you disturb its structure and you wash it. Better strategies. Things like phytoremediation are really exciting ideas, but they haven't really worked that well on demonstrated bigger scales. What we need are new strategies and new ways to do this. And what we're really interested in, sort of from our take on environmental remediation, is can we take biogeochemical processes, things that we know are happening already or happen in other places, can we take them and use them in environmental remediation? Can we manipulate these processes? So with that, I want to talk about biomineralization. So as I mentioned, biomineralization is the process by which organisms take something that's dissolved and turn it into a mineral. And biomineralization is life. Vertebrates, obviously, we have biomes, right? Bones and teeth. I'm really fond of having them. Things like corals are spectacular examples of biominerals. Shellfish, but plants do this. So these are roots that are taking copper and making little balls of actual metal from copper that's in solution. These are bacteria, species, all kinds of things, and even archaea are capable of making biominerals. And biominerals are really fascinating things, not just because organisms make them and because there's a real obvious, transparent link between organisms and the abiotic world formed by biominerals, but biominerals are unique. The organisms do them for some reason. They do things for the organisms. They provide structure, right? Without my biominerals, I would just be even more ready. They provide guidance. So there are magnetic biominerals that allow organisms to. They can use them as lenses to collect light. They scavenge nutrients for things. They can help organisms get rid of waste. Some organisms, take in iron and they essentially breathe it. They need to get rid of the iron oxide that's produced, so there's biominerals as a way to just dump that. They can provide others that are valuable to, like radiation resistance. Or they may do nothing at all, depending on what form, or at least nothing that we know at this point. Fascinating because they're different. So over here, this picture on your upper left is a calcite cube, and over here is a foram. And this crystal, the faces that are expressed on it are the exact same that are expressed on these shields, but they're in a different arrangement physically. So it's very, and of course it's at a very different scale, right? This is a hand sample and this is an SEM, so this is a tiny scale. There's nothing to, even though they have very similar ranges at the atomic scale, that says they're similar in what you would think they would behave as, right? If you looked at these two, this block of a mineral and this shell, you might think that they would behave differently and have different properties, and they do. Well, because they can be a little bit different than sort of abiotic things. What's more is if you make a mineral for environmental remediation, it's really nice to be able to make it with something else as opposed, like a microbe in the stream, as opposed to having to go dump minerals into wherever you're trying to clean up. It's also a cheap synthesis, right? Most, and organisms that are related to that, they don't require pay So it's pretty cheap to make these things chemically. The structure and crystallinity can be different. Obviously, the particle size can be different. We can have different morphologies. There's all kinds of differences in the physical arrangement of these molecules that could make them have different properties, which could make them either more advantageous or less advantageous for use in environmental remediation. And this is being done in some places. So this is an acid mine drainage treatment system right here, where it goes through a limestone bed reactor, and these black strips are where fungi are taking manganese oxides out of solution, or taking manganese out of solution, making manganese oxide. So this is being done in certain situations where you have minerals already. We like manganese oxides a lot in my lab. They're fascinating because they have lots of different potential crystal structures, highly reactive. They're very common environmentally, and they really influence the other biogeochemical cycles. So manganese can oxidize carbon, affecting the carbon cycle. Manganese can sequester metals by absorbing to the surface. So in that regard, they're very important in attenuating things like lead and zinc and copper. They're also, because they can bring in metal and they can do these oxidation reactions, they're also important for things like arsenic, because they typically can oxidize arsenic in the environment and other things that are metals like that. So chromium, arsenic, some oxyanions can be oxidized even if not absorbed very strongly, although I'll talk about that more in a little while. And again, this is useful because we need to understand how these biominerals, which can be common in the environment, affect transport of contaminants, and maybe we can harness them for use. So that brings me to the Superfund portion of the talk. So has anyone here been to Raleigh? A few people. If you came in through the airport and you drove down Wade Avenue, which is way in off of 40 into Raleigh, North Carolina, you would drive right past the arena where the hockey team plays and NC State's basketball team plays, as well as the football team. It turns out that's not the only sort of awful stuff going on there. It's not the performance of the athletic teams. There is also a former dump site. In 1969 and 1980, the university dumped all of its waste in unlined trenches that are where that red circle is. So keep in mind that sounds sort of bad, but this is a different time, different place, right? We didn't really understand necessarily what happened once we put them in the ground. A lot of places have dump sites like this. So a little slack for the past. Having said that, the site became a Superfund site when the population sort of grew up around it. Obviously, they dumped this waste here when there was like a here. This was the middle of nowhere. This was called Farm Lot 86. It was state property. There was nobody around. And Raleigh grew. And, now, right next to the football practice field and the area, there's a bank of solar panels here, and underneath the solar panels is where the actual site was. Yeah. So they've remediated the site by essentially capping that to try to stop its spread, which they have. But the trouble is there's a plume of legacy waste. So what I have here is an old EP report that shows the 2008 extent of a plume of chloroform. I show chloroform because it's a tracer. It says sort of the edge of the plume. The plume is, of course, like in nearly all sites like this, a complicated mixture of waste. Now, keep in mind that they don't really know exactly what they threw into this trenches, records of that sort of thing, because why would you? So, waste stream, and it lived the highway, and this is the main road in Raleigh. Population in Raleigh is a little under 500,000 now. The population is over 1 million. So this is a reasonably large metropolitan area, and this is sort of all of it. When we site, because it's been remediated. It's got a record decision. It's being cleaned up. Everything's good. Except when we went there, the system shut down because the system was biofouled. So the way it worked is there's an inlet that goes to like a process tank where it sort of equilibrates. It's taking this and you and the iron oxidizes and through a bag filter to take out the iron. And then it goes through an air stripper, and this removes most of the solvents that would be mixed in with the waste. And then it goes to another tank, and then they polish the water a little bit, and then let it equilibrate, and then it went out to a surface stream. It had been cleaned up to essentially drinking water standards at that point. So when we got called in, there was this black biofilm, sludge would be another word for it, that had formed on all the components. So we're very interested in what this stuff is. You can see this is a cap. This is a cap to one of the columns, and this maze-like pattern was me physically scraping sludge off with a falcon tube. So you can see how thick it was and how durable and how much is there. It's a nice lab coat. That makes us look very professional for our work in Superfund. I think pretty sure I am wearing a glove, even though you can't tell there. So we looked at this material under a scanning electron microscope, and we see tons of signatures for things that look like biological structures. Like these guys here look to be like fungal budding structures associated with reproduction. And we see some other here that looks to be of biological structures. We also see when we do a scan to look at the chemistry, energy dispersive spectroscopy. So that just gives you like a rough feel for what the chemistry is by counting electrons that bounce off this material and what energy they have. We see a huge peak for manganese. And it turns out this stuff appears to be a mixture of biomass and manganese. So if you know anything about the chemistry of manganese, it tends to be soluble in a reduced form. So manganese 2 tends to be soluble. And then manganese 3 and 4 minerals and be insoluble. But unlike, say, iron that oxidizes in air very rapidly, goes from iron 2 to the car rusty looking minerals we're with very rapidly, manganese doesn't do that on its own at normal pH. It needs a microbe to do it. So typically microbes take manganese 2 and take it to manganese 3, 4 minerals. That's what's going on. That's what these are. These are biominerals formed in it. And we'll get to more about them in a minute. Two sort of bits to this talk, two sort of segments. First is what's going on in this treatment system. And the second would be, is there stuff in this treatment system that we could use? So we mentioned manganese oxides are really important as oxidants potentially to break down carbon, break down maybe micropollutants, and also to sequester metals by absorbing them to the surface. Can we take some of the stuff we get from the system and maybe use it at some point? All right, so for the first part, what's in the system? We put on our, so I'm in crop and soil science. I was an environmental engineering major. My postdoc was in environmental science management and policy, somebody who was sort of a soil scientist, sort of environmental engineer, sort of a hydrologist. I don't know what I am. So what I decided to do was to take something that I call a geomicrobiological approach here. And the idea was try to figure out what the major forms of the oxides are and what is their effect on this treatment process. So we did some microscopy to try to look at biology and composition. We did some X-ray diffraction to try to understand the minerals that form here. We did some X-ray absorption talk about, which maybe you're familiar with, maybe you're not. It's a little more of a specialized technique, although there are some people here who are employing it. We did some, and then we did some microbiology. We cultured some organisms, and we some pyrosequencing to try to figure out what organisms were there. So X-ray absorption spectroscopy. Before I go any further, I want to give a bit of a primer on what it is. Basically, this is one of these techniques where there are 3 or 4 facilities in the U.S. we regularly go to. This is you do at a synchrotron. What happens is you take monochromatic X-rays and you shoot your material with them, and then you slowly increase the energy of those X-rays. When you get to a certain critical energy, the atoms in those, the atoms of one particular kind of element in your sample start absorbing those X-rays, and they kick out photoelectrons. So you get a big jump in what's absorbed. The stuff here where that jump is called XANES. Ocean spectroscopy is basically just a bunch of acronyms. So XANES. And what that does is it probes the properties of the atom that's absorbing. Basically, it gives you things like oxidation state. You can do a little bit of fingerprinting by comparing to what your unknown is. As you keep the energy of the X-ray that comes in, it affects the X-ray of the electron that comes out, and that electron bounces off all the atoms around it, and it essentially provides information about the structure of those atoms around it. So what you can imagine is it's a bell. If you ring a bell in a confinement, depending on how hard you hit the bell, you'll get weird and different interference patterns. And that's what you see here, is different ringing in the data. And believe it or not, that's meaningful and can tell you information about the structure of the material and the neighbors around what atom you have. So much so that you do mathematical magic. You can take this interference pattern from your bell as you change energy, and you can Fourier transform it, which is really the definition of mathematical magic, and it confirms, it forms to a radial distribution function that tells you sort of how many are in atoms in your material, your atom that absorbed the X-rays. What your atom is bound to, and you can also do printing where you take standards and kind of add it up and see what you have as well. All right, so with that primer, what you get is we want to know what the manganese oxides were. So we did X-ray diffraction, and unfortunately X-ray diffraction on manganese oxides is the most concrete data. So you get some information that sort of tells you you have maybe one. So then we went and did X-ray absorption spectroscopy. And these bottom three samples have dashed lines in red are unknowns from different parts of the system. And then we have some knowns that we made. And what it turns out is things up by linear try to reconstruct your spectra, your experimental spectrum. What we find out is we have layer-type manganese oxides. So this is for a number of reasons. One, layer-type manganese oxides have been shown to be made by other organisms before. So it's good that these fungi make them. A few other fungi made them, have been shown to make them before. Bacteria, this is what they make. So it's what we predominantly have. The other reason it's good is because these are super reactive. Very high potential to be oxidized, and they're very good at this. So these are very reactive components of a system. We have a smaller component of tunnel structure minerals, so I didn't have a diagram of them. These sheets here, this purple, is layers of manganese oxides, and this is sort of what the minerals look like if you blow them up very to atomic scale. The tunnel structures are less reactive. They have fewer sites that can bind metals, and they tend to be organic reactions. So the tunnel structures is more of a filler, and we're kind of glad we don't have as much of that. So the stuff we pulled out also has natively metals bound to it. Remember, this stuff. So everything that was, so this, in some ways, these manganese oxides have already reacted with whatever in the waste from the Superfund site. As it turns out, there are metals. There's things like cobalt, zinc, barium. There's a little bit of arsenic, a few other things as well. So we took some things we thought might be enriched in these oxides and tried to study them with the spectroscopy as well. So it's the same deal. We can add up unknowns, and what we find is that cobalt in it looks exactly like it does in model systems of manganese oxides that are of similar structure. And for zinc, we get something that looks very similar for about 75% of our signal, and 25% or less looks like it's bound to iron in the system as well. Because there's definitely some other things in this. Keep in mind, this is a sludge that we scraped off the inside of a tank. It's obviously not going to be purely one thing. So this was actually kind of cool for us because these manganese oxides that were forming in it were similar to things that other people had seen before when they were looking at manganese oxides made by bacteria. And we figured out that the metal binding was also fairly similar. We also did barium. Didn't put up the data because it's a little less compelling and a little more speculative. Barium is a little harder to deal with in terms of doing the spectroscopy. But all of our data suggests that this is similar to what you see if you did this experiment in a lab. If you took a model manganese oxide and you reacted with these metals, this is what you'd get. And that is a great result for us if you think about it. What you did in the lab, or what other people have done in the lab, is similar to what actually happens in a complicated waste stream with lots of different metals. So most people usually take one organism with a manganese oxide, take one metal, react, shake them around for a while in an ideal situation, take it and measure it, you get a particular form that you can study and say, haha, that's a model for the environment. It turns out in this case it's actually a pretty good model for the environment. And that's not necessarily always the case. So we were really excited about that. We also looked at the biology, and this was a surprise. So we tried to do culturing in this, and we cultured a bunch of different organisms that oxidize manganese. Basically, you go in, you put them on plates, and you see if the plates have manganese in them, and you see if you get a basically positive signal for oxidation of manganese. And what we found is that most of the organisms we pulled out of this treatment system were fungi. So typically when you culture organisms out of anything, you usually are thinking about bacteria. So we were really surprised. We talked to one of our collaborators who's worked in other systems that are metal contaminated, and most of the manganese oxidizing organisms in metal contaminated ponds, the pond sediments seem to be well, and in other really sort of difficult environments, the fungi seem to do better. So perhaps maybe because these are eukaryotes, not prokaryotes, perhaps these fungi do better in tougher environments, and that might be why we're seeing more of them. Could also be a culturing artifact, but I don't think that's the case so much. So we did an analysis to try to figure out how they classified, and we found out we had 6 different genera, fungi belonging to 2 different phyla, and that was really cool that we got 2 different phyla. And they make these really cool plates that have different patterns in them. You can see this one gets kind of a bullseye look to them, and they all look different. It's great. And we look microscope, and it's something out of a horror movie. You see these different shapes, you see different macrostructures associated with fungal reproduction, you see hyphae that look like crawling arms everywhere, but they all have different structures to them. You see spores, all kinds of different, these different structures suggest that they're going to interact with manganese in different ways because there's manganese in all of these, and there are manganese oxides in all of these different pictures. They might have different structures. We went back and did our X-ray spectroscopy. I'm not going to get too much into this, but all I'm going to say is that this second peak is sort of diagnostic to how much order there is in the manganese oxide. And you can see that this second peak varies quite a bit down all our different samples in terms of how big it is compared to the first peak, how sharp it is. And those 2 factors, how big that peak is and how sharp it is basically a proxy for how ordered this material is. The less ordered it is, the more likely it's going to be to absorb metals and react with organics. So we have a wide range of potential reactivities here, which is really great. So if we're interested in evaluating these organisms for their ability to take manganese oxides, to make manganese oxides that we could use potentially for environmental remediation to interact with organics and to absorb metals, we have potentially a wide range of candidates with potentially a wide range of reactivities based on what we've seen from our microscopy and based on what we see from this rough estimate of order. So that's great. So not only do we have a bunch of different organisms, the organisms are not all the same, biologically or in their sort of what they make. So we actually had too many of them. So to try to figure out what we're going to do next in terms of trying to understand what we're going to do for further investigation to figure out if these things would be useful, we chose 3. We chose a Paraconiatherium, a Copernella species, and a Coiniatherium. This was based on a couple different parameters. One was sort of how quickly they oxidize manganese. We didn't want to wait around forever, and if we're thinking about something that we want to potentially make manganese oxides in the environment or in a treatment system, we want it to be relatively rapid. And we also were looking at how different they looked microscopically in terms of the morphology and how different the oxides were. And we also had some synthetic oxides that we decided to carry forward into our study. So the next thing we really wanted to do was evaluate the properties of these materials to see, with an eye on how they might perform for environmental remediation. And again, we've dropped our geomicrobiological approach, although we have stolen the type of slide here. And now we're really trying to figure out structure reactivity. And we're going to use some of the same techniques. We want to really understand the structure of the mineral. We understand how it binds metals, so absorption isotherms, to understand the binding capacity of these minerals. And then we also want to understand how they might interact with organics. So what we can do is we can do some actual experiments with organics, but we'd like to generalize that a little more. So also we're going to do some experiments. We do electrochemistry. Okay, so, and this is all, remember, just to estimate the reactivity of some of these different oxides. So what I have here is a time course of a quinone with a manganese oxide. So a quinone is this ring structure here that has a couple hydroxides coming off of it. And we react it with manganese oxides because it's a special molecule in some ways in that it's a probe. It doesn't stick to the manganese oxide surface. It stays in solution, and it's capable of transferring 2 electrons. If this stuff is a manganese 4, 2 electrons would make it manganese 2, and the manganese 2 would dissolve. So it's a 2-electron transfer probe, and we have a material that we would like to react with these probes to see how fast they react. And the idea is that if we can probe their fundamental redox chemistry with these probes, it should be a proxy for other organic matter. So this time course has micromolar on the axis, and then we have time in seconds. So this is not very long for the course of this. So right here would be 10 minutes. And what we see is, as soon as we introduce our manganese oxide to these quinones, manganese starts to dissolve, the quinone starts to go away, and our control experiments, nothing happens. So from this, we can get a rate and try to understand how fast the material reacts. So that's great. We have this way of chemically measuring a rate that we think is a proxy for how fast these manganese oxides would react with organic contaminants. We also want to know more about their fundamental reactivity and if we can relate it to these chemical rates. So what we did is voltammetry. And voltammetry is a chemistry technique where essentially electrons in a material and pull them back out. And see if you can oxidize and reduce the material, and you can see how fast that happens, and you can see how hard you have to. So basically what we did is we took this electrode, this is made of carbon, our oxides on it, we dried it, and then what you do is you apply a potential and try to reduce the material, and then once you think you've reduced the material, you cycle the potential back the other way and try to reoxidize it. And hopefully you get a reversible cycle like this. So an interesting thing about this, and this is why we have collaborators, because some of this is a bit beyond me in the theory, but if you vary the rate at which you push electrons and pull them in, these peaks move around, and if you see how that moves, those peaks move as a function of changing that scan rate, you can calculate how fast the electrons are being transferred into the material, which is an electrochemical rate of reduction that you can compare to your chemical rate of reduction. So we do this for a couple different manganese oxides, and we see this loose correlation. We were a little surprised by this. We thought it would be tighter than this. But there's some sort of relationship, but not that much. So the question is, the first question you ask is the data good? At least that's what I always ask of my own data. And I think the answer is yes. I think the data is pretty good. I think these points actually are where they're supposed to be if you did the measurement again. So the next question is, why don't they correlate better? And for that, we need to think about the structure of the manganese oxides a bit. So it turns out there are a couple different sites on manganese oxides where reduction can happen. If you remember, they were little layers. So one place where reduction can happen is the edges of those layers. So it can attack the outside of the particle from the outside. The other part is holes in those layers. So if you think about them, what they really are is it's a dinner plate. And then if you turn the dinner plate aside, the dinner plate has holes in it. So it can attack the edges or it can attack the holes. So maybe this says there's some difference between the edges and the holes. And maybe one affects one more than the other. So what we did to try to study that, and as an attempt to study things more complicatedly, is we tried to study how metal absorption affects our redox chemistry. And as a bonus, we get to understand how these manganese oxides absorb different metals. So that's great for remediation purposes, right? Because one thing is if we want to know how much they absorb metals, potentially for remediation, we get this measurement. If we want to know how these metals affect redox chemistry, well, we need this information anyway. So it's a win-win for us. So we took zinc and we put quite a bit of it, if you look here, almost one-to-one, onto a manganese oxide. And what we have here is a synthetic down here, and then we have 3 fungal oxides. And the fungal oxides seem to absorb a fair amount more. We can go in and do our X-ray spectroscopy again. And I swear this is the last one of these squiggly dots. And what we have here is a bunch of these different and then we have a couple standards. And this standard is bound to a mineral in a particular configuration, right here. And then this one is bound to organic that's similar biomass of the fungi that's associated with the manganese oxide. And what turns out is we get a mix. We fit this and maybe 70 to 20% of it's on the oxide itself, and maybe the rest of it is on the biofilm. So some of this extra capacity is because it's binding the organic matter, this zinc. But the rest of it is binding the biofilm. And what's more, and binding the manganese oxide. And what's more interesting is the zinc only binds, and I'm not going to get into exactly where it comes from this data, but I would be happy to talk about this. It only binds to the holes. So it doesn't bind to the edges of the dinner plate, it only binds to the holes in the dinner plate. We can do the same thing with arsenic. And I felt like I had to put up an arsenic slide, and this is the only one I had. I try to please. So this is arsenic 5 absorbed to the same oxides. And what you can see is that the synthetic does a little better here. It's in the range of the different biogenic oxides, and we get a lot less here, although there's still a fair amount absorbed here. I said I wasn't going to show you any more squiggly lines. It's because the ones for arsenic are the most lowest quality, and you might as well stick with your good stuff, especially if I'm starting to wear you down by looking at squiggly lines. I'm just going to tell you that we know from that data that the arsenic only sticks to the edges of the dinner plate, not the holes. And this agrees with other people's data that have tried to look at sun synthetics. So what we can do is we can take those samples we had and first compare the data and find out that the zinc absorbs to a larger extent than the arsenic. So it sticks to it better. And that actually makes a lot of sense. The zinc interacts more with the biofilm than the arsenic does. So some of it absorbs the organic matter. But the manganese oxides tend to be really negative surfaces. So really negative surfaces tend to bind cations that are positive and bind things like arsenic that are anions less well. Different manganese oxides, meaning there was a different order to which had the maximum absorption capacity for arsenic versus zinc. So that means that if we go back in our data, copernellus is the big winner here, paraconitharium, then coniotharium, and then the synthetic. Whereas here it's paraconiotharium, coniotharium, and then the copernellus. So the order is different. So that suggests that some of these different manganese oxides have different relative abundances of sites. So some may be bigger and less edge. Some may have more edge and fewer holes. So that's cool. That's great. They have different structures. The XF data says they absorb at different sites, so that's good. So how does that affect the redox reactions? Well, the answer is we don't have this information for the biogenic at the moment because we're having a lot of trouble getting the biogenics to stick to the electrodes when we have metals on them, and we don't completely know why. But we can do it with the synthetics. And it turns out if you have an electron transfer rate from the voltammetry, here it's 20. If you put the zinc in, it drops to 1.2. So that means the zinc sitting on that whole site on the top of the plate slows down the reaction considerably. And that's the same case for two different synthetic manganese oxides. What's interesting, though, is you put arsenic in, which only bonds to the edge site, it also slows down the electron transfer reactions. So it means potentially you can get electron transfer reactions at both sites, and that bonding to them can both of them down. So that's interesting to us. And we still need to do this with the chemical experiments. This is a hard thing to do with the chemistry because you need to make a lot of doped metal to work with. So you need to take these manganese oxides and then do wet chemistry on them. Requires a lot of material. So it's a little bit harder to do. So I want to sum this up. I provided a lot of non-arsenic information here. So I want to really make sure it understands why it's important. And the answer really is, let's think about using these things for environmental remediation. We've already tried to make a case they could be important, right? We've got these organisms that can live in a complicated, nasty waste stream. They can make manganese oxides. Manganese oxides can break down a wide range of organic contaminants. Phenols, chlorinated compounds, antibacterials, dyes, chelators, pesticides, synthetics, a whole bunch of things in the environment. And they can react with the manganese oxide and they get oxide. If these metals are absorbed to the surfaces, they may not react anywhere near as quickly since it seems like they may shut down the rates of electron transfer. But, and this is an important side benefit of that, the manganese oxides were to oxidize these organic compounds, reduce the manganese oxides become manganese 2, which is soluble, and the oxides would fall apart and release whatever metals were held. So by shutting down these oxidation rates, at least the metals are stuck with the manganese oxides. The manganese oxides aren't going to go away. So the manganese oxides may not behave well as a magic bullet for both treating metals and organic. You may be able to treat one, or maybe do it in stages in some way. And in that case, it may actually be more suitable. Okay. So to sum up and finish off as my job as opening act here today, I want to drive home a few points, and that fungi isolated from the Superfund site produce layer-type oxides. And there's a whole variety of different oxide structures that are subtly different that we seem to be able to produce. Because they can exist in these waste treatment streams, they may be useful in design remediation systems where we can incorporate them into a treatment. The absorption capacity and the redox capacity are not that different from what we see for synthetics. And absorption to the manganese oxides by things like zinc and arsenic that absorb to specific spots may inhibit the redox reactivity to different extents depending on how they're bound. And that creates a trade-off because the absorption of these metals slows down the redox reactivity, which may impede the ability of manganese oxides to break down organic components. But they'd be more likely to keep them in more of a long-term storage if they don't react. And that's pretty much what I have to say. I'm going to acknowledge a few folk here. National Science Foundation supported some of this, including a grant from the environmental chemistry and REU. We've had a Barnard student in our REU program, so just a quick advertisement there for anyone who's interested. We've done our work at Stanford for doing the radiation work, and we have a bunch of people who have helped us by either sharing logistics. And with that, I'd like to open up to any questions. Yeah.
Yes. So fungi versus bacteria. What are fungi just as difficult or easy to manipulate in the lab as bacteria are?
Yeah.
The first part. The second part, thinking forward to some in situ method, would they travel less far than bacteria? That does look like pretty wild forms?
So the first question I think is, are they easier or harder to work with in the lab, fungi versus bacteria? And the second one is sort of their suitability in a remediation system compared to bacteria. Does that sort of sum it up?
Specifically for in situ.
For in situ, yeah. So the first thing is they're a bear to work with in the lab compared to bacteria. Bacteria almost behave like little chemical factories. It's great. You put them in solution for manganese oxidizing. 24 hours later, you get all these little bacteria covered in manganese oxides. And it's great. And they behave relatively reproducibly until they stop, and then you have to go back to your stock and redo them. But they work. Fungi take a long time to oxidize, a couple weeks. They form a nasty, sludgy stuff. There's much more biomass compared to the bacteria, so they are way harder to work with in the lab. They also do all kinds of strange things, and they're gross. Bacteria make like a nice suspension. Fungi, you'll have like layers of things on them, and yeah, it's anyway. The other side of it though is, although they grow slower, it's a negative. I think they might be more suited for environmentation because of what you said. They are much harder to sort of a fungal biofilm than it would be a bacterial biofilm. It's more durable, and they're less likely to undergo ecological succession quickly. I think that if you have a fungal community that's set up, it's probably going to be relatively stable. Bacterial communities, if you set this up somewhere, it could pretty quickly, I think, be overwhelmed and lose its ability to oxidize manganese, which I think is one of the reasons it hasn't been done more often. Do I have a student?
Yeah, there's one on the webinar.
There's one on the webinar.
So, Steve Spade and then Megan Belvini. In New Jersey, we see radium, a cation absorbing into manganese oxide water treatment media. Any idea on how to get the radium out of manganese oxide?
So I have no particular experience with radium. Sorry, should I reread that? So there was a question about radium absorbing the manganese oxides based on it being seen in absorption media in New Jersey. I have no specific experience with radium. You could resolubilize the manganese oxides, which basically means you could dissolve them with some sort of reductant. But I would be happy to learn more about this problem if they want to contact me offline. That seems like a pretty specific question. I got two in the front row. Arm wrestle.
Could you go back 2 slides?
The answer is maybe. There we go.
Yeah, so I guess the idea here is that oxygen of these actors on the left side is a good thing.
Mm-hmm.
But how would we know that the oxidation products aren't as bad or worse than this one?
So this is a list of compounds from a recent review, and the mechanisms for most of the breakdowns of these things are pretty well known. So if you knew specifically what compounds were there, you could go in and look up in the known database and see sort of what's typically produced. So I think in some cases you do get some nasty intermediates, but I think a lot of cases you get things broken down a fair amount more. I think the other answer to that is if you have any particular thing you're concerned about, you could always do a lab study and try to do the prediction before you use this as a treatment. Yeah.
I ask this, as a biologist,
Yep.
Distant expert on metabolism of drugs, and we often, or environmental chemicals, and we often, in the process, make them worse.
Classic examples of that with pesticides all the time. Yeah.
So my question relates to this slide too. You sort of say it shuts off here, but then you also said that the absorption appears to operate in both cases. To me, that suggests a galvanic reaction. For those in the audience, that means a redox reaction where the oxidation and the reduction happen in different locations. So you actually have a circuit going through the mineral. For me, that's really cool to think about for manganese because it means with light, you can actually cause the radium to speed up, and you could actually by applying a specific frequency of light, you could actually preferentially react specific bad actors. And do so at fast rates. Or other ones, things that you may not want to oxidize, and you wouldn't oxidize. So you could, it allows you an engineering pathway that could be more useful.
There is photochemical reactivity. You have to shine a lot of light on it, but it's potentially possible. I completely agree with you. There's a paper where they did quick X-ray spectroscopy on cobalt, and cobalt tends to go into manganese oxides. Basically, it goes from cobalt 2 to cobalt 3. Cobalt 3 is exactly the same size as manganese 4, and it tends to just end up in the hole where the manganese oxide was, so it fills that hole. Their study indicated that the oxidation happened from cobalt 2 to cobalt 3 happens at the edge, and the incorporation happens at the hole. So potentially, there could be an electron passed. It's potentially not the same atom, is sort of what I think is the implication, even though they never came out and said it. So potentially, you could have electron transferred from here to here, and then the drop-in, as opposed to the old model, which basically was it all happened at the vacancy.
So we'll end our first talk. We have cookies and coffee we'll do a 5-minute break, and then we'll do the second talk. We'll start at 4 o'clock. Okay. Okay, sounds good. Thank you.